Next, I will need to define a minimum and maximum length for the LCD nets. With our rule updates completed, we can now go back to the layout and route these critical nets. So using interactive routing, I can click on one of the differential pair nets and start routing to its location, and it will automatically grab the other and pull it with it. I can now select all the LCD nets, use the sketch router to draw a path where the nets need to be routed, and the auto router will complete those nets in that location. With the nets routed, we can go ahead and auto length match all the nets. Once the nets have been tuned, I can select them and use the target length dialog box to verify that they've all been matched within my requirements. Moving on to the next section, I want to control the fan out on these capacitors, so I'm going to draw in a trace and a via. Once completed, we'll select the trace and the via and go ahead and use copy paste to add the remaining. Next, we're going to define our plane areas on the board. Using automation, we don't have to draw our plane shapes. With dynamic capability, we can just use the route border that we defined at the beginning of the design. On this layer, we do need to add an extra plane area for another net, so we can go ahead and draw in a shape, and then the dynamic capability will take over, filling in that plane area. We can make a quick adjustment, and it automatically corrects. The BAT- pin that we drew this plane area for is also high current, so we need to adjust the thermal connections to the plane. We can do that by selecting the pin and then creating custom thermals on the fly. Before we move on to manufacturing, I want to do some electrical verification along with additional DRCs. So let's go ahead and take a look at that LCD net that we did a hyperlinks analysis on when we were capturing the schematic. From the analysis menu, we'll go ahead and choose Export to Hyperlinks. This will create a complete model of the board and open it up in BoardSim. Once in Hyperlinks, I can select that net, open the oscilloscope, and do a verification. From the simulation results, it looks like we're good. Now that we've done our verification, we're going to go ahead and send a model over to the mechanical engineer so they can review the part placement and also do thermal simulation. Seeing we've been in communication with the mechanical engineer already, we don't want to create a baseline. We want to create a proposal which will only send the new content that's been added since we've started the layout. After performing a quick refresh to make sure we have all the right content, we'll go ahead and add a quick comment about what's being sent and create our collaboration data. Our mechanical engineer can now import the data we just created using the collaboration app from within Solid Edge. We can see the entire board imported with components and traces, but we don't quite see the plane, so let's go ahead and turn off the outer shell of the PCB to expose the internal plane areas. With a quick visual inspection, we can see all the plane data appears to be there. Switching over to the 3D view, we can do a quick visual inspection of the board inside the mechanical enclosure. Before we move on to generating manufacturing data, let's go ahead and take a quick look at Pads Professional's Rigid Flex option. To start this Rigid Flex design, we're going to import data using the collaboration interface. With our Flex and Rigid board outlines imported, we now need to define each one of the Flex area regions. We do this because we can assign different stack-ups per area. I've already gone ahead and defined the stack-up for this board, so you'll notice the cover layer, adhesive, and stiffener have been added already. So we're simply going to choose the layers that will be part of this LCD Flex area. If we go ahead and hit the View Stack-Up button, we'll get a quick view of the layers being used for this Flex region. With our stack-up areas defined, we can now go ahead and start creating our bend areas. To do this, we go to the Draw menu and choose Bend Area. We now create a rectangular shape that represents where that bend is going to be placed. From the Properties dialog box, we can set things like the radius, the angle, the width, where the bend area origin is, and other various settings required or that can be used for Flex design. With one of our bend areas defined, we can now jump over to the 3D view and see what our bend looks like on our Flex and how it fits with inside the mechanical drill housing. Before we move on to routing, let's see what happens if we place this resistor on the Flex. Pay close attention to the pad geometry that's being used on the rigid part of the board and what it looks like on the Flex. Notice how the pad shape automatically turned to rounded corners. If we go look at this in the 3D space, we'll also notice the cover layer is using rounded corner openings. Pads Professional handles this by adding special Flex pad stacks to the component. And when it detects it's in a Flex area, it automatically swaps out the standard ones for the Flex ones. Now we can go ahead and route traces from the flex fingers up into the printed circuit board. To simplify this process, we're going to use a feature called multi-hug trace. As you can see in the tooltip video, this feature can use other objects as a template to draw your traces. So here we're going to use the flex outline as a template. With only a few clicks, we've added all our traces. Now we can complete the finger to the trace with a couple simple routes. With our routing done on the LCD flex, let's go ahead and add the stiffener now that's going to be required in order to mate this flex with its connector. We'll turn on the drawing shape that we've had off previously. We can then select the shape that was already there, turn it into a stiffener, and now it will be represented as that when we look at it in the 3D view, and when we output our documentation. Before we move on, let's go take a quick look at the design in 3D. So we'll turn on bends, and we can see how the flexes are currently formed, and then we can turn on the housing of the drill body to visually see how everything fits. Alright, we've come back into work after checking our design the night before, so we need to check the design back out, and we'll finish our DRCs up and go ahead and output our fabrication data. From the main toolbar, we'll go ahead and activate our batch DRC. You'll notice that it'll already come up pre-configured because of our batch DRC function, like many other features within Paths Professional. You can create schemes so you're not having to readjust everything on the fly. After performing our DRCs, we're now ready to output our fabrication data. Instead of using Gerber, we're going to go ahead and output ODB++. This file format creates an intelligent database for fabrication and assembly. With a quick review of the data we're going to output, we'll go ahead and create our content. With Paths Professional, we can review the data after it's been exported. So we've turned on the ODB++ viewer, which will load the data that we've just created automatically. With the ODB++ viewer, we can turn layers on and off to see exactly what our fabricator is going to see in the end. And if you still like to use Gerber, this viewer offers a ODB to Gerber comparison to show you that the Gerber data has exported exactly like the ODB++. Now that we've exported our manufacturing data, we'll do a manufacturing check using Siemens PCB Flow. So from our project overview tab, we'll click on Create Project, and we'll give this a name. You can give it a description as well if you like. We continue on to the next step where we'll import the actual ODB content. So we upload our file. So just take a second to upload the data. We can then do upload and continue. Next, we're going to choose a fabricator's design rules that we want to verify our design against. In this case, I'm just going to use our test one here, PCB Flow. Then hit Run Analysis. PCB Flow is free for any customer that creates an account, but with limited reporting capabilities. If you want to expand your reporting capabilities, you can purchase a subscription. With the analysis now complete, we can click View Report. A new tab will appear with all of the report information. To filter through items shown in the main part of the window, we can click on Layers and then Constraints. Let's go ahead and click on Layer 1, and then from the Constraints drop down, we'll click on Plated Through Hole to Plate. So here we found a warning, but not an error. We know that because this yellow triangle that's showing up here at the top. If it was an error, it would show up as red. We can see the actual measurement that the tool found, and then down below here we can see the design rule in which it's checking against. Because it's below 10, which is preferred, but not below 8.5, this is just a warning. If you want to know more about any one of the constraints that you select, you can hold your cursor over the I button, and it will give you a complete description of what that verification is checking for. If we want to navigate back to where this error is, it gives us the exact coordinates of where that error is occurring. So we can click on this icon here. This will copy those coordinates, and then I can go back over to Paths Professional. We'll zoom in, and then we can use the ZC key-in command, paste in our coordinates, and we just need to put a comma and get rid of that space, hit enter, and it will take us to that exact location that the DFM report is showing as an issue. Now again, this was not a design rule failure, it's just a warning. We can also export a report that we can email to colleagues or to keep with our records for this design. Once a report's created, you can go ahead and click on that.